So welcome back, everyone. It is my pleasure and my honor to be chairing the part of the afternoon session. So our first speaker is Marc Hindry. Marc Hindry is professor at the Institut Mathématique de Jussieu in Paris, at Université Paris-Cité. He's an expert in Diophantine geometry, in particular famous for proof of generalization of the Manin-Mumford statement. And in general, an expert in heights, so heights on abelian varieties in particular, with also very nice results on lower bounding heights for elliptic curves. So outside of being an excellent mathematician, he's also an excellent advisor, as I can say. And so he got his PhD in '86 under the supervision of Michel Laurent, and his habilitation in '91. Marc will talk about zeta functions applied to arithmetic Diophantine geometry.
Thank you, Fabien. So it is a pleasure and a double honor for me to speak here in front of the Royal Swedish Academy and in honor of Enrico Bombieri, a mathematician whom I've met almost constantly throughout the years, be it analytic number theory, but of course Diophantine geometry, and even in algebraic geometry. So the topics is that I chose is connecting zeta function with Diophantine geometry. So perhaps I can start with just like Enrico did some time ago. If you sum up so -2 plus 3 minus 2, then you get pi squared over 6. As you all know, if you sum up 1, 1, 1, 1, 1, you get minus 1/2. And if you sum up the 2, 3, you get minus 1/12. That's Euler. Of course, so I will call this special values of zeta function. Of course, this is zeta of 2, this is zeta of 0, and this is zeta of -1. So this was actually the first topic on zeta function, finding special values of the series, or of course the analytic continuation of the series. And then, as Professor Bombieri reminded us, there is let's say the work of Riemann and Dirichlet is much more oriented towards analytic properties of those zeta function, so analytic continuation, and especially the zeros. So for Riemann, what was missing actually in Riemann's paper is the fact that the zeta function does not vanish on the line real part equals 1. And in Dirichlet's paper, what was proven and important was the non-vanishing at s equals 1 of the what is called today Dirichlet's L series. So I want to talk about something that sort of mixes analytic. So perhaps for this theorem, I should add the name of Adama and de la Vallée-Poussin. Which continued the work of Riemann and Dirichlet. So I have nothing special to say about analytic estimates. You had a much better expert this morning. The topic I want to discuss is how you can mix these special values for zeta function with analytic estimate to get strong results in Diophantine geometry in general. Really, the paradigm for this is the so-called Brouwer-Siegel theorem. So I will start with this. Brouwer. So I want to give the statement, so there's no zeta function in the statement, but the proof relies on zeta function. So I will give a slightly simplified version there. Sure. So the Brauer-Siegel theorem is a theorem about number fields. So I will pick number fields. So my simplification is I will take them with a fixed degree of a Q. You can make also the degree tend to infinity, but it's a bit more complicated. And then you have, well, basically the most basic invariant of a number field is its discriminant. So I will call it delta K. Actually, I will take the absolute value of the discriminant. Of course, for example, for a quadratic field where you add square root of d, the discriminant is either d or 4 times d. And you have two much more elaborate invariants that are very important. One is hk, the class number. So that's the number of ideals modulo principal ideals. It's the finite group that measures the defect of unique factorization in the number field. And you have the regulator of units, or unit regulator, which measure, in some sense, the complexity of the units in the ring of integers. And a first rough statement of the Brauer-Siegel theorem is that the product of these two quantities, which are both very complicated, and when you look at examples, are sometimes very small, sometimes very large. They behave in a kind of random, chaotic way. When you take the product, it really looks like the square root of the discriminant. That's a rough statement of the Brauer-Siegel theorem. So a more precise description is the following. I'll write two inequalities, hk, that will be smaller than, well, some constant times square root of delta times log delta to the power n minus 1. So n is the degree of the field. And the lower bound, well, the known one is something that depends on, well, you have a constant that depends on epsilon n, and you can put here delta k to the power 1/2 minus epsilon. So, of course, in that, I mean that for all epsilon, there is a constant c epsilon. This is a very strong statement and a difficult theorem. If you look at examples, you can see right away that it says a lot about the arithmetic of. So if I will look at 3 examples. If you look, that was the original actually problem, the problem of Gauss. If you look at imaginary quadratic fields, then it says that the class number behave approximately like the square root of d. So in particular tends to infinity, of course. If you look at a real quadratic field, then what it says is that the class number of this field times the logarithm. So I will write explicitly the regulator as this is just one unit that generates a whole group, and you take the log of it. That behaves like the square root of d. I should mention that it's very difficult to separate the two. For example, we don't know if there's infinitely many real quadratic fields with bounded class number. We do know that there are infinitely many with small unit, so with very large class number. But very small class number and large unit is a mystery. There seem to be a lot, but it's really not known, and even the conjectures are not very clear. I'll give a third example, is if I take K, a CM field. So a CM field is, you have first, I will call K naught a totally real field. So all of whose embeddings are real. And K over K naught is a quadratic extension, and that is totally imaginary. So there's many reasons to look at those fields. I will mention one further on. Well, for these fields, what happens is that, well, in general, as I said, it's very difficult to separate the class number and the regulator. So you get an information about the product, but not about each term. So in that case, you do get an information for the, I mean, the main point is that the regulator are the same. Well, are the same. There's either a factor, the factor is on this side. It's either 2 or 1. So since I'm doing asymptotics, I will consider them to be the same. So if you take the quotient of the two, you get an estimate for the class number, and when you wind up things, you get that the class number grows at least like the discriminant to the power 1/4 minus epsilon. So it's not an equivalent, but it's one of the very few cases where you can prove that the class number has to go to infinity. And maybe I will talk more about this later, but I should mention that this is one of the essential features in the Andreault conjecture, who will be one of the subjects of Jonathan's talk later. So these are the three examples I wanted to quote. Of course, there is oh, so epsilon is any positive number. That means, oh, epsilon is the unit. So if I take the ring, if you want let's simplify saying that this is the ring of integer. If I take the units, it's generated by plus or minus 1. This unit to the power m for m in Z. It's, of course, special to real quadratic, or you have also some cubic fields where the group of units is cyclic, or biquadratic fields. For other fields, the unit has a larger rank. And so this unit, essentially, maybe I can quote that. This is epsilon d equals u plus v square root of d. So it's the smallest solution to the classical Fermat or Pell-Fermat equation. So actually, this statement says something about the smallest solution to the Pell-Fermat equation. Well, it gives a bound for it, because this is at least 1. And it says that, well, if the class number is very small, this smallest unit is very, very large, because it's exponential in the square root of d. So this is, I hope I have given a description of the statement of the Brouwer-Zegons theorem. Now you notice that there's no zeta function in the statement, but the proof goes through the zeta function, and the zeta function that occurs. So I don't want to call it a proof. It's a sketch of a proof that I will give. It uses the Dedekind zeta function. Which is, well, after Dirichlet's L function and Riemann's zeta function is the next one in the zoo that Enrico mentioned. So the zeta function, well, you can write it exactly like except that you take ideals and the norm to the power minus s here. So you take non-zero ideals. So well, I will write OK for the ring of integers of the number field. Or you have, of course, the Euler product, where you take the product over minus the norm, power minus s minus 1. So that's over non-zero primes. I will call them prime ideals. So this zeta function, of course, satisfies almost the same properties as the classical Riemann zeta function. It converges absolutely for a real part of S strictly greater than 1. It can be extended to the whole complex plane. And it has a simple pole. It has only one pole at S equals 1. But yes. Now, the Riemann zeta function has a pole at S equals 1, but has a residue that's not so interesting. It's 1. Well, one can consider that 1 is a very interesting number. But the residue, so what I will call the special value at S equals 1. So by definition, it's just the first term when you write the Taylor expansion, the first term that's non-zero. So in that case, it's the residue at S equals 1. The formula is the following. It's called the class number formula. It's the class number times the regulator over the square root of delta k, and then some small factor. Well, they turn out to be small, so I will just write them quickly. And here, well, I will just write in a fancy way. So for those who don't like schemes or algebraic groups, this is just a group of units. So I'm writing, integral points on the multiplicative groups. That's just the torsion part is just the number of root of unity. It's just that later you will see something similar appearing. So that's just small numbers. Since I have taken the degree bounded, they are like constants. So in the class number formula, in the residue appears the three quantities that we want to look at. So that would be the first step. So that's what I call, like Euler, the special value, computing the special value of zeta function. And of course, the second step is analytic estimates. So it's the proof of, well, in that case, the proof is that delta minus epsilon, C epsilon, is, you have a lower bound like this and an upper bound like this. The upper bound is actually not that hard. The lower bound is really the deep part of Siegel's theorem. So Siegel proved it for quadratic number fields, and Brouwer extended it to general number field using his generating character theorem. Surprisingly, some 20 years later, Stark proved that actually the essential difficulty is with quadratic number fields. So I can be a bit more precise. Siegel's zeros have already been mentioned, so I can mention if if there are no Siegel zero, no, sorry, in French there is an accent, not in English, you can get a bound that is much better, that I will write like C1 over log delta. And even better, this constant C epsilon is not effective. You cannot give any specific value. You only know it exists. Whereas this C1 is not only the lower bound is much better, but it's entirely effective. You can make it completely explicit. And of course, you can get even better estimates if you assume GRH, but not that better. I mean, you can replace the log by log-log, which is interesting, but with GRH. Here you only need to know, I will make the drawing. You draw a small circle. You go to 1 minus 1 over log delta. So you know that there are no zeros here, no zeros on the line. But you also note that in this small disk, there is at most 1 0. It has to be real. And that's what is called a Siegel zero. Well, up to the constant. That can vary. So if there's no Siegel zero, you get a much better estimate. The advantage is that it is known, for example, it is known that, I've already said it in one sentence, is that only quadratic fields can produce Siegel zero in this context. So if you have a number field which do not contain a quadratic field, there are no Siegel zero. So this, well, you can say a lot, or it depends how you count number fields, but there are lots of number fields for which this is true. Let's say cubic number fields, this estimate is true. So I always find, well, people have their favorite. This is one of my favorite theorems. I won't say it's my favorite theorem, but it's one of my favorite theorem in the sense that you have to introduce tools that are, in some sense, outside the scope of the statement of the theorem. And it mixes, of course, in the proof of this, there's a lot of algebraic number theory. And of course, in these proofs, there's a lot of analytic number theory, especially in the lower bound. So in some sense, that's the things that I'd like to generalize to other contexts. You know, so the idea is construct a zeta function, find a special value, estimate the size of the special value, and deduce results from that. So unfortunately, in many cases, you have to accept some conjectures. Well, it's difficult to have full proofs. But I want to give three applications of this principle. So the first one has nothing to do with my work, but I find it very, very beautiful. The two others is things that I have worked out, sometimes with collaborators. So the first application would be, well, to bound the height of elliptic curves with complex multiplication, or even better, abelian varieties with complex multiplication. So I'll give details concrete about elliptic curves, and I'll assume for the rest that you know what an abelian variety is. So an elliptic curve, well, let's say to simplify, I will take it over Q, but it's over Q bar. Otherwise, there won't be many. So you can always write an equation like this for the elliptic curve with a point at infinity. Then you have the so-called J invariant, which is a cube over 4a cube plus 27b squared. Actually, for the expert, there's a small constant that I omitted, but it plays no role here. So I will decide to call C naught a small constant that has no importance, but that is fixed, that has a specific value. So what this invariant tells you is when two elliptic curves are isomorphic over the algebraic closure, if they have the same J invariant. So I want to say something about the height of the J invariant. So if we take any elliptic curves, there's not much to say. It can be any algebraic number, so it can be anything. If the endomorphism ring of the elliptic curve is not just multiplication by n, so we say that E is a CM for complex multiplication, then it is a very interesting problem to bound the height. So here I will take the nice definition, the height of the J invariant. So height, I will only briefly, if alpha is a rational number with co-prime numerator and denominator, the height of alpha is just the log of the maximum of P and Q. Of course, if it's an algebraic number, you have to work a little bit more to define, but it's essentially the same definition. So we would like to, well, there is a, let's call O this ring. So if it's not Z, then it is an order in the ring of integers of an imaginary quadratic field. So let's call M this index, and then it's natural to define the discriminant of O as, well, M squared, the discriminant of the field, well, the field Q of I square root of D. Now, what we would like to show is to have a bound for this height in terms of the discriminant. And this is precisely what is shown or known, has been known for some time. So you can put here C epsilon, the discriminant of O, to the power epsilon. So this is the statement that I'm aiming at. So this is a purely Diophantine statement, but as far as I know, the only proof goes through essentially the special value of an L function, more precisely the logarithmic derivative. This becomes even more interesting if one looks at an abelian variety. Of higher dimension, so of dimension, say G. So what does it mean to be a CM in that case? Well, you have to be a bit more precise than here. I will call O, the analog of O is the center of the endomorphism ring of the abelian variety. And so A is CM means that well, I will call it the dimension of well, O tensor Q over Q is 2G. So here, for elliptic curves, we had a quadratic field. For an abelian variety of dimension G, it's not exactly always a field of degree 2G. It could be a product of field, but the total dimension being twice the dimension of the abelian variety. Then there is a statement that says that the height, I will write it like this, the height of A is smaller than C epsilon, the same, well, the same, essentially the same statement, except, of course, that the height has to be defined a bit with more sophistication. The discriminant of this is an order in a ring or a product of ring of integers, so that the definition is the same. So I write it like this. I like to write it like this because there's still no zeta function in this, but in the proof of it, there is a zeta function. I will explain later. So perhaps I can. There's a third one. Yes. No. Can you? Can I? Ah, yeah. That's what I need. Thank you. So for the moment, I will leave it like this. This is the first application I want to discuss about this. So this is perhaps I should give names. Well, there is something called the Kolmez conjecture. Well, I will state only the average Kolmez conjecture, which was proven by Andreata, Goren, Howard, Badapoussi. And in a almost simultaneous paper by Yuan and Zhang, different papers, slightly different methods. And this was used by Jacob Zimmermann to prove the so-called André-Oort conjecture for, well, the moduli space of abelian varieties. So it's one of the ingredients, but it's actually the essential ingredient that Jacob Zimmermann added to the work of Pilar Zimmermann. Well, there's plenty of names you will hear on the André-Oort conjecture. So I will first give the list of the three applications and then give more details where there's a zeta function appears here in the proof of that statement. My second problem will be also with abelian varieties. It is the so-called Mordell-Weil theorem. So again, if you're not familiar or don't like abelian varieties, you can stick with elliptic curves. The statements are already very, very interesting. So I will take K now to be a number field. So I will speak of the number field case, or I will take a function field that is the fields of function over a curve over a finite field. So that I will call the function field case. Then the statement of the Mordell-Weil theorem is the same in both cases, is that this group is finitely generated. That is, we have a finite group, the group of torsion points, and then we have a finite number of generators, all independent. And of course, I will call R the rank of this group. Well, there is naturally a height, a canonical height on this. So to simplify, I will assume that I'm given a principal. Yes. Principal polarization. So I will call L a principal polarization, which you don't really need to know what it is. What you need to know is that this produces a canonical height that I will call HL. I will forget the L, which is a quadratic form, which is quadratic. Okay, positive definite. Maybe I have to explain what I mean by positive definite. I mean that when you tensor with R, so AK tensor R, so this is a finite, real finite dimensional vector space. I mean that the quadratic form is positive definite, because otherwise the height, of course, is 0 on all torsion points, so it contradicts a little bit the positive definite, but that's what positive definite means. And this height is like some height, so like some Weyl height. So what we would like, of course, we have a finitely generated group. We want to have bounds on the height of the generators. So that's the question. Bounds. Oh, this one has. For the height of generators. So, of course, I mean, so I will put a question mark. I should say right away that this is an open problem, but I can, well, at least I can propose a reasonable solution that will be conditional. So you notice that, of course, when we speak of bounding the height of generators, we mean, of course, you have generators of any height. You can take multiple, well, you can take P1 plus 1,000 P2, and so there's no bound for all bases. You want the smallest bases. And so a better formulation is a bound for the regulator. So the regulator is, I will write it like this, is the determinant of, since we have a quadratic form, we have a scalar product. So this one, I will write the L here. You want a bound for this quantity. So this classical geometry of numbers tells you that if you can bound this volume, then you can find a bound for the height of generators. So the conjecture that I would propose is the following: is that the regulator of A over K, I'm leaving some space here, is smaller than, well, again, I will put a C epsilon. I will put the height to the power 1 plus epsilon. So what is this capital H? Well, this in the number field case, it's exponential of the height of A. So I'm sorry because I have not defined the height, the Falting's height, but that would be a bit too long. It's something like the height of the J invariant for elliptic curves. And so that's for the number field case. And in the function field case, I will take Q to the power, well, what would be the Falting's height, the degree of the sheaf of relative differentials. That's the function field. That's the function field case. And the theorem, if you want that, I will explain, is that if you have BSD plus GRH implies this statement. So BSD is the famous Birch-Swinnerton-Dyer conjecture. It's another $1 million conjecture that no one knows how to solve. Still, I have quoted the function field case because you can go much further in the function field case. First of all, the generalized Riemann hypothesis in this context is true, is known. It's essentially the linear theorem. And the Birch-Swinnerton-Dyer conjecture is known in many cases over the function field. So you have an upper bound like this, let's say, for many over function field, for many abelian varieties. So I will leave this that way. So this was my the second problem I wanted to quote. The third one, the third one to have some variety is a statement about I will take S, a surface. So it's more something like algebraic geometry mixed with arithmetic. I will assume that it is smooth and projective, which is not asking too much. It's just that we have a nice geometry on that, and define, well, the problem makes sense over any field, but I will work over a finite field. And here is the problem. We have on the surface we have curves. And we know how to define the intersection numbers of two curves. So it actually belongs to Z because, well, you take up to deformation to have complete intersections. And if I define the Néron-Severi group as the group of linear combinations of curves, so things that can be written as sum of NCC. So C is a curve, and NC is in Z. And of course, the sum is finite. And I take this modulo deformation, well, which is, from the point of view of algebraic geometry, is natural to define. If you can parameterize continuously with an algebraic variety the deformation of curves, you get a space like this. And the theorem of Néron-Severi says that this is a finitely generated group. So you have, again, a torsion group, and then you have a finite number of curves that will generate the group. So I will call, let's say, I will keep R. R will be the rank of the neurons every group. And now I have again a regulator that I will call the regulator of S, or S over FQ, which is, well, first I take the determinant of the intersection numbers. Now there's a sign, and I'm not interested in the sign, so it's easy to determine the sign, but I'm not interested in it, so I take the absolute value. And we ask for a bound for this. It's something, in some sense, that measures the complexity of the geometry of the surface, and we would like to have a bound for it. So in terms of what, well, you have a bit of a choice. I will choose what is called the geometric genus. So the geometric genus you can define as, well, the first cohomology of the sheaf of differentials, omega 2 of S, or the H2 of S OS. Let's say, to be concrete, if S is in P3 of degree D, this PG is D minus 1, D minus 2, D minus 3 over 6. So that's rather concrete. So what is my guess for the guess is the regulator of the surface should be smaller than Q to the power PGS times 1 plus epsilon. I should be careful. So first I put a question mark. The other thing is that it cannot be true for all surfaces. It's quite easy to see that if you use blow-ups or this kind of thing. It can't be true. If it's true for one surface, if you blow up sufficiently many times, it becomes untrue. So it cannot be true. So you have to put some conditions on the surface. Well, let's say, for example, all these conditions are satisfied if I look at surfaces in P3. Then there's no condition at all. So I have stated my 3 problems, and I hope I made it clear that there is some kind of analogy with the Brouwer-Siegel theorem. Now I can make the analogy much more precise. As I will add here something like that is like the class number. What is like the class number is the so-called Brouwer group of S over FQ. What I can prove is that if this group is finite, then this inequality is true. Unfortunately, I don't know how to prove that the Brouwer group is always finite. So here the statement will be that finiteness of the Brouwer group, which is known in quite a bunch of cases and is conjectured to be always true, implies the statement. So that starts to resemble the Brouwer-Siegel theorem, and the strategy of proof essentially is the same, is to have those quantities appear as a special value of an L function, and then to estimate the special value. For the abelian variety, case, actually what you have to put here is the cardinality of the so-called Tate-Shafarevich group. and then that should be true. And more precisely, so in the function field case, the fact that the Shafarevich state group is finite is enough to imply the conjecture. Over number fields, unfortunately, there's only finitely many abelian varieties or ellipticals for which the version has been proven. So unconditional statement that there's none, because you need at least an infinite family to have a statement that is meaningful. GRH is not as bad, because if you, that's actually to get the correct exponent that I need GRH. If you don't have GRH, but you still have, let's say, analytic continuation, for example, for elliptic curves of a Q, you can get things with an exponent 3 instead of 1, which is not the correct exponent, but at least, so you only need Birch-Sonnenson-Dyer conjecture. So in the remaining time, I will give a bit more detail. So perhaps I'll start with this one, and then I'll see how much time I have left. Okay, I will erase this. So I look at, so I want to state the so-called average Kolmez conjecture. So you can state it like this. So I have, I will call, did I give a name to my field? No, so F be a CM field. And let's phi be a CM type. So what is a CM type? It's a subset of the set of embedding of the field F into C. That satisfies two things. That's first, if there is one embedding, the conjugate is not in the set. And the union of the two is the whole, so phi union phi conjugate is the whole set of embeddings. So you take G, let's call FQ equals 2G. So that's the Shimura-Taniyama theory. You take G embeddings. In each pairs of conjugate embeddings, you choose one. So you have 2G, obviously 2 to the power G, such CM types.
The set is different from phi.
Yeah. Okay, I will write it better. This would be. Is that better? So I will call. Let us call A F phi. An abelian variety, so of dimension G, with, well, I will write it like this. The ring of endomorphism F is included in the endomorphism. So most of the time it will be equal, but you could have products as they generate case. Then there's plenty of such abelian varieties. They're not isomorphic, but they all have the same height. it's not a trivial theorem, but it's known, it's part of the work of Kolmes. So the average Kolmes conjecture can be stated like this. You have so you take the sum over all phi, the 2 to the power g phi's of the height of this h a phi. And this is equal to, and now comes our zeta function, which had disappeared. So it's actually the logarithmic derivative at 1 of L. So plus 1/2 of the log of the discriminant of the field over the discriminant of its, so I didn't write again, so what I call F naught is the totally real subfield of F. So plus a constant time G, essentially, well, you can add a constant for the Faltings-Height and make this constant disappear, or if you have chosen a constant to define the Faltings-Height, then another constant disappears. It plays no role here. So what is this, and what is this L function? I will give two formulas for it. So this L chi S, well, it's a Dedekind zeta function of F over the Dedekind zeta function of F naught. So of course the poles at 1 cancel. It's a function that's holomorphic at S equals 1. What is the character? You can also, it's not difficult to see that you can write it like this, norm of P minus 1. So it really looks like a Dirichlet, a quadratic Dirichlet character with chi of pi equals plus 1, minus 1, or 0. That's if P is split in the quadratic extension, if it's inert or ramified. So there is, I mean, the full Kolmes conjecture is a formula for the individual height, but it's not proven. What is proven is this average, and it's enough to get a bound for each of the heights. So from this you get that the height of any of these is bounded by this quantity, because well, up to a small constant, all of the Faltings height is positive. So this quantity is exactly the thing you want. And now you have to estimate this. And this precisely Ziegel's theorem tells you. So you have Ziegel plus a little bit of Brouwer implies that this derivative is, well, essentially it is 1 over 1 minus beta plus O of log, the log delta F of delta F0. So if there is a Ziegel 0, if there's none, then you forget about this term. You get exactly what you want. If there is a Ziegel 0, then you need Ziegel's theorem that tells you that the Ziegel 0 is a little bit far away from 1. So you get that this is smaller than df delta f over delta f naught to the power epsilon. And of course, if you have no Ziegel 0, then you can get O of log delta, which is much better. And it turns out that, okay, this estimate exactly what you need for André-Roth conjecture. This estimate with epsilon is enough. So perhaps I should, yeah, sorry, I'll stop here.